Hello everyone, welcome back. So today in this video we'll be talking about your let me just- classical linear regression model. Classical linear regression model, also called CLRM. So we have talked about your linear regression model already. We know what this is. So just adding another term to this, that is called your classical. Classical because it was or the idea was given by Mr. Gauss in the 1860s, I guess, or 1821 it was. Yeah. So till then we've been using this model. So this model is called your classical regression model because it has certain assumptions. Okay. So assumptions relating to your method of least squares. So there are seven assumptions that we follow or that we assume while estimating your least squares, and that is why this model is called your classical linear regression model, because it's still based on the idea given by Gauss in 1821. So there are other models also which do not follow these assumptions, and they are not called classical linear regression model. Okay, so this is your classical regression model, and it's like very helpful in econometrics. So like we'll see like in the upcoming videos how this is helpful and how these assumptions are really important for us. So these assumptions will help us navigate through the essence of econometrics initially very smoothly, and lately we'll see how these assumptions get broken and what are the impacts or effects of those broken assumptions. Okay, so let's move ahead. So why do we need assumptions? The first question should come: why do we need these assumptions? So the idea is fairly simple. So in our model, yi equal to beta 1 plus beta 2 x I plus ui. Okay. So in our model, your ui depends on both xi and ui. So if I vary any of the two values, xi or ui, my yi values changes. Okay, right? So unless we are specific about how xi and ui are created, okay, so we have to find these. We have to create these values. We have to choose these values, and corresponding to these values, we have xi values and we also have ui values. Okay. So unless we are specific about how xi and ui are created or generated, there is no way we can make any statistical inference. Okay. So assumptions made about xi variables and the error term are extremely critical to the valid interpretation of the regression estimates. So we have to make certain assumptions about your ui, your xi, okay, and other parameters of the model or other aspects of the model, so that the relations that we are trying to capture is clear and concise. And if you don't follow these assumptions, so there might be some uh, arbitrariness in the computed values of yi corresponding to your xi values. Okay, so we'll see how these assumptions will help us and its uh, role in our further econometric analysis. Okay, so let's talk about the first assumption. So assumption one, it says model is linear in parameter. So I'll not discuss this assumption because we have already talked what this means. Okay, and it is linear in parameter, so it can be non-linear in terms of the variables. Okay, so this is the first assumption. Then I have your assumption 2, and it says that the values of the values of x are fixed beforehand, or x is equal to non stochastic. Okay, so this is done basically for our convenience. So if I already have the values of x, like if I talk in terms of the examples that we had discussed, so if I already have the income level, weekly income level of say 10 families, so it is easier for me to compute the related values of their consumption, weekly consumption at that given level of income. So I'll choose the families which have that given level of income, and for those families I'll compute the level of consumption. Okay, so because if I don't have these fixed x values, then there can be a range of values of x, and it might be very difficult for like to gather the data for the entire range of these x values. So it just makes the task very easier. The task of data collection and computation becomes very easier if I have this assumption. Okay, so it is more realistic to have x values as fixed, right? So if the values of x are non-stochastic, we get a different model, which is called your neoclassical model. Classical model. Okay, so that if x is non-stochastic, we'll have a different model to work upon. So in the case of CLRM, your classical linear regression model, my x is stochastic. Okay, x variable is stochastic. Now I have assumption 3. So it says 0 mean value of UI. So the expected value of your UI term is 0. Okay, so it can be written as UI given xi is equal to 0. This also implies of yi given xi is equal to beta 1 hat, beta 1 plus beta 2 xi, because this term becomes 0. Okay, or simply we can write e of ui is equal to 0. No matter what the value of xi, my ui is equal to 0, right? For that xi. So it means that overall, for any xi, my ui in general is equal to 0, right? So if I have to show this graphically, what this means, so this is my regression function. This is x1, this is x2, this is x3. So I have a range of ui values. So the average or expected value lies on the, or is equal to 0. So the expected value of y lies on the regression line itself, and that is why the expected ui value given xi is equal to 0. So this is true for every x, right? This is true for every x. So this is what it means. I hope this is clear. So this means that the factors not explicitly included in the model and therefore subsumed in UI. So the factors that might affect UI but which were not a part of the model, okay, so which were assumed to be a part that was subsumed in UI, okay, do not systematically affect the mean value of UI. So your mean value of Y, okay, is not being affected by the UI values. Okay, so overall, so some positive UI, some negative UI. So the overall effect of these values gets cancelled out, and the model is typically, or dependent upon your x variable. Y is dependent upon your x variable. Okay, so E of ui given xi equal to 0 implies there is no correlation between these two terms. Okay, so if x ui and xi are correlated, it is not possible to assess their individual effects on ui. So yi is equal to beta 1 plus beta 2 xi plus ui. So my yi is being affected both by xi and by ui. So if both these terms are correlated, it means that xi is being affected by ui. So I'm not able to calculate the individual effect of xi upon yi, because xi itself is being uh, affected by ui hat ui values. Okay, so my purpose of this regression model is to estimate the impact of xi upon yi. Okay, and if these two terms are correlated, this effect will not be captured, this individual effect will not be captured, and that is why we have made this assumption. Okay, this is your third assumption. Then there's a fourth assumption. It says assumption 4. So it talks about homoscedasticity. So this simply means homo means same, skedasticity means dispersion, dispersion or scattering. So this means constant variance of the error term of the term ui, regardless of regardless of xi. So mathematically it is variance of ui is equal to expected value of ui minus expected value of ui given xi ka whole square. So this is the formula of variance. Okay, so it becomes expected value of ui square given xi, uh, because we know that e of ui given xi is equal to 0, and since we know this, so this terms become this. Okay, which is equal to sigma square. So this variance across all values of x is fixed. So this is an assumption that we have made. So this is called the assumption of homoscedasticity. So this simply implies that y population corresponding to various x values have the same variance. So I'll try to explain this graphically. What this means is, so if I try to make a three-dimension graph, okay, let's give it a best shot. Okay, and right. So try to look at in three dimensions. Okay, so this is your x, this is your y, and this is your probability density of ui. Okay, so and this is your regression line, right? And for corresponding x1, x2, x3 values, so let me change the color here. Uh, so the variance of the, so this peak or this spread or the variance of the ui or the error term is basically the same. So this uh, bell-shaped curve is same for all the values of xi. Okay, so the peak and the spread is similar in all the cases, in all the values of xi. So why this is the case? Why this is the case? So we'll talk about the reason. So this is simply because if variance of ui given xi, or so if say variance of given x1 is less than variance of u given x2 is less than variance of u given x3. Okay, if this is the case, then the likelihood of y observations coming from the population with x equal to x1, so the likelihood of y values coming from the population when x is equal to x1 will be much more closer, much more closer to the PRF. Okay, so if this spread, or this spread around the regression line is small, so it means that the y values that we are getting, so this is basically the spread of the y values which is captured by the ui term. Okay, so if the spread is less, and okay, if the spread is less, it means that the y values are more closer to the expected value of y, or the value that is lying on the regression line. So this is closer to that. So when I say that this there is homoscedasticity, it means that all the values of y that I'm getting, the dispersion around the regression line is similar for every xi value. Okay, for every xi value, whatever y values I'm getting, the dispersion around the regression line is similar in all the cases. Okay, so this is important. It means that the spread of y values uh, is similar. So it is not like in some cases there is very large dispersion around the regression line, and in some cases there is a very small dispersion around the regression line. So it is similar. It is similar. So we'll see how this will help us in the future videos. So this was your, so just one point. So variance of ui is equal to sigma square. This also implies variance of yi given xi is equal to sigma square. So this is basically capturing the dispersion or the scattering of yi values given the xi values. So that is also equal to sigma square. So both of these terms are similar in that sense. So now we have your assumption 5, right? So it simply says no auto correlation. It means that your two error terms given to xi values are uncorrelated. So suppose I have ui comma uj for xi comma xj. So the correlation, this is given, the correlation between them is equal to 0. Okay, this is also called no serial correlation. Okay, no serial correlation. So this is also an assumption. So what it means is, so if I have to plot 1, 2, 3. So if I plot, so this is plus ui, this is minus ui, this is plus ui, this is minus ui. Similarly, plus ui, minus ui, plus ui, minus ui. This is also plus ui, minus ui, plus ui, minus ui. So this graph is representing between positive correlation between the two error terms. This graph is representing a negative correlation between the two error terms, and this graph is showing no correlation. So as uh, the value of ui is increasing, the value of uj is also increasing, and similarly uh, on the other side, that is on the third quadrant, uh, in this case, as the value of ui is increasing, the value of ui is decreasing, so there is a negative correlation. Uj is decreasing, so there is a negative correlation. In here we have no correlation, so this is what we want. We want no correlation between the two error terms. So suppose why we are doing this. So suppose we have a prf which is, say, yt at any time t, beta 1 hat plus beta 2 hat xt plus ui, okay, plus ut. So suppose I have a population regression function which looks like this. So I, through this assumption, I'm saying that my ut term should not be affected by any ut minus 1 or ut minus 2 or ut minus 3 term. Okay, so my current y value in this time period t should not be affected by, or should not be affected by any uh, error term of the previous time frame. Okay, so if what this means is, if there is a correlation between ut and ut minus 1, it means that it will affect this value, and this in turn will affect this value, your yt value. So there should be no auto correlation. So these this ui ut and ut minus 1 should be independent. So this is what it means. So our model should not be affected by the error terms of any other time frame, like in this particular example. So this is example is in a way trying to explain why this assumption has been taken. Okay, so now we have the sixth assumption. So it says that the number of observations n should be greater than greater than the number of parameters to be estimated. So it is more of an intuitive assumption. So if I have x, if I have y, and if I have beta 1 and beta 2 be estimated, so I have two parameters. So it says that the number of observation n should be greater than at least 2 in order to have a significant uh, assessment possible. Okay, so this is what it means. So you should have some observation in order to estimate your beta 1 and beta 2. Then I have assumption 7, that is the last assumption. So it talks about the nature of x variable. So it says that the x values in a given sample must not all be same. So it is very obvious. So you can't have the same x value or the same level of income, weekly income, and based on that you can't estimate different levels of consumption of different families, because then you'll have the same types of families for that given income level, and that will give you the same result. So you will not, so this you will not get a regression line, you'll just get a single point. Okay, in order to have a regression line, you must have different x values. Okay, that is why this assumption is important. It also says that your x values should be similar, and there should not be any outlier. Okay, so suppose if you take 80, 100 and 120 as the weekly income of families, and based on these income you try to calculate or estimate or try to gather the information about their weekly consumption. Okay, so there should not be a case where one of your x values is say 2 lakh dollars. Okay, so because if this value comes into the model, then the result that we get, or the y value that we get, will create will also be a very large value, and this will and my model will be dominated by outliers. Okay, so the expected value of y would be dominated by this y value that I get from this 2 lakh weekly income observation. Okay, and these all these assumptions are basically true for your population regression function. Okay, population regression function, PRF. Okay, so these are not true for your SRF, these are true for your PRF, whatever assumption we have made here. So this was all about your assumptions of the CLRM model. I hope it was able to impact or generate some understanding. uh, that's all for today, and see you in the next video. Thank you.